Okay, so I want you to now check your work on the rock type analysis from the Himalayan mountains in Nepal, which does include Mount Everest, the tallest peak on our planet. And so you have analyzed this. And this is a topographic map which shows elevation. I already have shared that with you, but let me explain a little better. Do you notice how they almost look like bullseyes, these little circles? And so those circles that are matched are showing matching, or that are connected are showing matching elevation. So as the circles get smaller and smaller, like the center of the bullseye, that's the tallest peak. And so you can see right here is the tallest overall, which is Mount Everest. So the first thing that I wanted you to do was look up and remember some things in some cases about the 6 rock types that make up Mount Everest. And so I simplified it a little bit. You can see that this granite is called leucogranite, and this is a yellow band marble, but the main rock type there is marble. So really check your work carefully here. Limestone, we know that is a sedimentary rock. You might have remembered that. Well, what does it mean to be a sedimentary rock? That it had to be eroded chunks that got smushed into layers. And we know that those rocks form at the bottoms of lakes and oceans because rivers take those sediments into the lakes and oceans. Then we had marble in the Himalayan mountains. And marble is a metamorphic rock, meaning that it's changed form by heat and pressure. Then there was another metamorphic rock, which is schist, still changing form by heat and pressure. And I will share with you, I developed this lesson new for this year. And I had to look up what migmatite was. And I found that what it is a mixture of igneous and metamorphic, and that it's generally metamorphic rock that's been intruded by magma, and then the magma's cooled. So a mix of those two. Granite is definitely an igneous rock formed from cooled magma. And remember, we pronounce this metamorphic rock gneiss, that it's a metamorphic that's also changed form by heat and pressure. So after you've looked up and analyzed these rock types, our next step is to figure out what is the most common. And we do see all 3 rock types represented here, but for sure the most common is metamorphic. Now, why does this make sense to us that we would have lots and lots of metamorphic rocks within the Himalayan mountains? And the answer to that is the pressure. So doesn't it seem to you like metamorphic rock formation, the pressure of it, remember with the clay models when we push down, that would have something to do with mountain building, that mountain building would be a pressure-filled process. And so our next question here, what do we notice is the rock type that is at the peaks? And so if you look with me, there's Mount Everest, but you can also see 3 other peaks next to it. And we see those in brown. Brown is marked with limestone. Okay, so whoops, here it shows up. So you should definitely have that one for question number 3, that limestone is at the peak of the mountains. Now you should be feeling a little bit of shock about limestone at the top of the mountain, because remember, it's sedimentary, and sedimentary rocks are formed at the bottoms of lakes and oceans. So it should be making you go, how did the bottom of a lake or ocean get all the way up to the tallest peak? And then it gets even more puzzling. When you did a Google image of limestone, this is the first image that comes up. I found another one similar. What do we actually see there? Now, this is question 4. We see fossils many times embedded in limestone. Class, the work that we did in class with fossils, and some of you did that digitally, we have limestone here. It has ocean fossils in it. What? They have limestone at the top of Mount Everest with ocean fossils? That is absolutely true. Now, questions 5 through 7. What does this mean? Well, those are not lake fossils. Those are ocean fossils in that limestone. So the top of Mount Everest, once upon a time, had to be the bottom of the ocean. And so could there have ever been an ocean 5 miles high? The answer to number 6 is no. That would go against gravity. The water never was pulled that high up. What that means, though, is the top of Mount Everest, once upon a time, had to be very low elevation. So what does that mean about the plates then? Scientists said there are 3 boundaries: push, pull away, and slide by. So how could the ocean floor get 5 miles high? It's a definite push together situation. Literally, the ocean floor, kind of like a conveyor belt, was pushed, and thrust that high into the atmosphere. So, our next question is this plate motion, this pushing, that, and think about it, the pushing, we see evidence of that with the pressure of metamorphism, with metamorphics being the most common rocks. And certainly it's the explanation for how limestone could get on the top is this pushing. Well, is Mount Everest still growing? Now, I know that this data is old, back from my high school years, but this trend is still continuing. Notice that we do see, and this would be the first data interpretation question, Mount Everest growing. Not a lot, a centimeter per year. The centimeter is less than half an inch, but it is still growing. So what does that indicate to us? It tells us, my goodness, those plates, they still must be pushing together. So the rate of the plates pushing is greater than the erosion rate at the top of the mountains. Our next step after this is to go ahead and do our Nepal travel.